Picture this. In 50 years, massive mirrors floating in space redirect sunlight away from Earth, while underground cities house billions of people and machines literally pull carbon dioxide straight from the air. This isn't science fiction anymore. These are real engineering solutions being developed right now to save our planet. Today, we're diving into the most ambitious planetary engineering projects ever conceived, and some of them might blow your mind. What if I told you that humans are about to become the architects of Earth itself? That we're on the verge of technologies so powerful they could reshape entire continents, control the weather, and even move mountains? The problems facing our planet seem insurmountable. Climate change, overpopulation, resource depletion, rising sea levels. But engineers and scientists around the world aren't just sitting back and hoping for the best. They're designing solutions that sound like they came straight out of a blockbuster movie. Let's start with something that sounds absolutely crazy, but is actually being seriously considered by some of the world's brightest minds. Solar radiation management. Imagine launching millions of tiny reflective particles into the stratosphere, essentially creating a man-made haze that reduces the amount of sunlight reaching Earth's surface. Or picture enormous mirrors positioned between Earth and the Sun, each one the size of a small country, deflecting just enough solar energy to cool our planet by a few crucial degrees. The science behind this is surprisingly straightforward. When volcanic eruptions like Mount Pinatubo in 1991 shot sulfur dioxide into the stratosphere, global temperatures dropped measurably for several years. Scientists realized they could replicate this effect artificially. Harvard researchers have already conducted small-scale experiments, releasing calcium carbonate particles from balloons to test how they interact with the atmosphere. The particles would scatter incoming solar radiation while allowing heat to escape back into space. But here's where it gets really wild. Some proposals involve creating space-based solar shades. These wouldn't be single massive structures, but rather swarms of lightweight autonomous spacecraft positioned at what's called the L1 Lagrange point, about 1.5 million kilometers from Earth. At this location, the gravitational forces of Earth and the Sun balance out, allowing objects to remain stationary relative to both bodies. Each spacecraft would be essentially a smart mirror, capable of adjusting its position and reflectivity based on real-time climate data. The engineering challenges are staggering. We're talking about launching millions of tons of material into space and coordinating a fleet of spacecraft larger than any human civilization has ever attempted. But the potential payoff is equally massive. Computer models suggest that blocking just 2% of incoming solar radiation could offset the warming caused by doubling atmospheric carbon dioxide levels. Now let's talk about something happening much closer to home: direct air capture technology. Companies like Climeworks in Switzerland are already operating facilities that literally vacuum carbon dioxide out of the atmosphere. Their machines use massive fans to pull air through chemical filters that grab CO2 molecules and separate them from everything else. The captured carbon can then be stored underground permanently or used to make synthetic fuels, concrete, or other products. The current facilities are relatively small, capturing thousands of tons of CO2 per year, but the vision is to scale this up dramatically. Imagine industrial parks covering hundreds of square kilometers, filled with nothing but carbon capture machines powered by renewable energy. Some proposals suggest building these facilities in remote areas like the Australian outback or the Sahara Desert, where land is cheap and solar energy is abundant. The math is encouraging. The atmosphere contains about 850 billion tons of CO2. Removing even 10 billion tons per year would make a significant dent in atmospheric carbon levels. That would require roughly 1 million of today's largest direct air capture machines. It sounds like a lot, but consider that humans manufacture about 80 million cars every year. Mass-producing carbon capture technology isn't fundamentally different from mass-producing automobiles. But what if we could go even further? What if we could engineer entire ecosystems to maximize carbon absorption? Enter the world of synthetic biology and ecosystem engineering. Scientists are developing genetically modified trees that grow faster and absorb more CO2 than natural forests. They're creating artificial coral reefs that not only provide marine habitats, but also sequester carbon in their calcium carbonate structures. Some of the most ambitious proposals involve rewilding entire continents. The Pleistocene Park project in Siberia is already experimenting with reintroducing large herbivores like bison and horses to restore grassland ecosystems that disappeared thousands of years ago. These grasslands, it turns out, are incredibly effective at storing carbon in their root systems. Scaling this approach could potentially restore grassland ecosystems across millions of square kilometers in Russia, Canada, and Alaska. The engineering doesn't stop at the surface. Underground, we're developing technologies that could revolutionize how humans live on Earth. Boring Company and similar enterprises are creating tunnel networks that could house entire cities below ground. These aren't just transportation tunnels, but complete underground urban environments with residential areas, commercial districts, and industrial zones. Underground cities offer multiple advantages for a warming planet. The temperature below ground remains relatively constant year-round, reducing energy needed for heating and cooling. Underground structures are naturally protected from extreme weather events like hurricanes, tornadoes, and heat waves. And building downward instead of outward preserves surface land for agriculture and natural ecosystems. The technology for large-scale underground construction is advancing rapidly. Tunnel boring machines are becoming larger, faster, and more efficient. New concrete formulations can withstand the pressure of deep underground construction while providing excellent insulation. Advanced ventilation systems can move fresh air through kilometers of underground passages without requiring massive amounts of energy. Japan is already leading the way with underground urban development. The country has extensive networks of underground shopping centers, pedestrian walkways, and transportation hubs. Tokyo's underground city spans dozens of square kilometers and houses shopping malls, restaurants, offices, and even small parks. The technology and expertise gained from these projects could be applied to much larger underground developments designed specifically to house populations displaced by climate change. Speaking of displaced populations, let's talk about floating cities. As sea levels rise and coastal areas become uninhabitable, engineers are designing entire urban environments that float on the ocean. These aren't just luxury resorts for the wealthy, but practical solutions for housing millions of people. The Seasteading Institute has been developing prototypes for floating cities that could be completely self-sufficient. Solar panels and wind turbines provide renewable energy. Desalination plants produce fresh water from seawater. Hydroponic farms grow food using minimal space and no soil. Waste processing systems recycle everything from human waste to plastic garbage. The most advanced designs feature modular construction, allowing floating cities to grow organically as populations increase. Individual housing modules, commercial buildings, and industrial facilities would all be designed to float independently, but connect together into larger communities. If one area becomes overcrowded, sections of the city could literally sail away to establish new settlements elsewhere. The engineering challenges are substantial, but not insurmountable. Modern ships already demonstrate that large structures can remain stable in ocean conditions. Oil platforms show that complex industrial operations can function reliably at sea. The main hurdles are economic and political rather than technical. But perhaps the most mind-bending concept of all is atmospheric engineering. What if we could control the weather itself? Cloud seeding technology already allows limited weather modification. By introducing particles into clouds, we can trigger rainfall in drought-stricken areas or prevent hail formation over agricultural regions. Future atmospheric engineering could go much further. Massive arrays of ground-based lasers could heat specific portions of the atmosphere to create artificial high-pressure systems, steering storms away from populated areas. Ionospheric heaters like the HAARP facility in Alaska demonstrate that we can already manipulate the upper atmosphere using radio waves. Scaling up these technologies could potentially give us precise control over regional weather patterns. The implications are staggering. Imagine being able to prevent hurricanes from making landfall, to bring rain to deserts, or to clear smog from polluted cities simply by adjusting atmospheric conditions. The engineering required would be on a scale never before attempted by human civilization. But the potential benefits are equally unprecedented. Of course, all of these technologies raise serious questions about unintended consequences. Atmospheric engineering could have effects that ripple across the entire planet. Underground cities might disrupt groundwater systems. Floating cities could impact marine ecosystems. Space-based solar shades might affect global weather patterns in unpredictable ways. That's why many engineers emphasize the importance of starting small and testing extensively before implementing planet-scale interventions. Small-scale experiments allow scientists to study the effects of these technologies without risking catastrophic unintended consequences. The timeline for these technologies varies dramatically. Direct air capture is already operational and scaling up rapidly. Underground construction technology is mature and ready for large-scale implementation. Floating cities have functioning prototypes and could be deployed within a decade. Atmospheric engineering and space-based solar shades remain largely experimental, but could become feasible within 20 to 30 years. The cost estimates are equally varied. Building a network of carbon capture facilities large enough to significantly impact atmospheric CO2 levels would cost trillions of dollars over several decades. But that's comparable to what the world already spends on military budgets or fossil fuel infrastructure. The economic argument for planetary engineering becomes more compelling when you consider the cost of not taking action. Climate change is already costing the global economy hundreds of billions of dollars annually through extreme weather damage, agricultural losses, and health impacts. Those costs will only increase as the planet continues to warm. Investing in planetary engineering technologies today could prevent far greater expenses in the future. What's truly remarkable is that these aren't distant dreams anymore. They're engineering problems with concrete solutions being developed by real scientists and funded by real investors. Companies are already raising billions of dollars to commercialize direct air capture technology. Governments are seriously studying atmospheric engineering proposals. Private organizations are building prototype floating cities. The next few decades will determine whether humanity becomes a true planetary engineering species. The technologies exist or are rapidly developing. The economic incentives are aligning. The environmental necessity is becoming undeniable. We stand at a pivotal moment in human history. For the first time ever, we have the technological capability to engineer our entire planet. The question isn't whether we can do it, but whether we will choose to do it responsibly and effectively. The decisions we make in the next 10 years will determine the fate of human civilization for centuries to come. These engineering solutions to Earth's problems represent humanity at its most ambitious and creative. They show that when faced with existential challenges, human ingenuity doesn't give up. Instead, it dreams bigger, builds better, and finds ways to reshape reality itself. The age of planetary engineering is just beginning, and it promises to be the most extraordinary chapter in the human story.